other videos, the lecture videos I have uploaded, and I have sent the links to your batch representatives. I think I have sent this one maybe today morning, I think maybe around 3 a.m. Okay, during that time I finish all these things and I send this tutorial also. Sometimes that they might not seen those things, so maybe you are referring that one. Chamath and Insaf will share all these links with you. I have already sent these links to Chamath and Insaf. I think they will share those things with you.
Good morning, sir.
Yeah,
Just now I see that.
yes.
Yeah,
Okay,
I will share with the.
not your fault that actually I sent this one maybe around 3 a.m.
Yeah, yeah. I will share with the batchmates now.
Thank you.
Okay, sir.
Okay, then here we can prepare this table, and we have to find this one, A plus B plus C column. And we can make this one. This is 0 here. This is 1, 1, 1, 1. And then we can make B plus C. B plus C here, it's 0. Here B plus C 1. This is 1. And this is 1. Here again, this is 0. 1. Okay. Then we can make A plus B. A plus B, this is 0, 0, 1, 1, here 1. Okay. Then we can make this column. This one we can make. This is now we have B plus C here. We have to take operation between this B plus C and this A. Okay. And this one, when we take O between this one, this is 0. Here it's 1, 1, 1. And for this one, it is 1, 1, 1, 1, 1, like that. Okay. Next one we can take this one. This is A plus B and C. This is 0. And this is 1, 1. Take these 3, then X, Y, Z. From the table, you can see that X equals Y equals Z. Okay. Like us, we can prepare the same type of table for AND operation also. AND operation means that this one, A plus. Again, you have to make a table like this, then we can make this column and these two columns. Then we can show that all three columns are equal. Okay, this question, it has small mistake here. Here timing diagrams are missing. Okay. Sorry for that mistake. I'll use the timing diagrams. Okay, these are the timing diagrams. These are the inputs A, B, and C. How can we do this one? Shall we write the output equation for this one? This is AB, and this one C bar. Then this is AB plus C bar. Yes. Okay. And here this is AB and this is C bar. This output is, sorry, AB is coming from this side. This is C bar. And this is AB, C bar. There are many methods you can use to draw these timing diagrams here. But actually here, when we draw these ones, that we have to prepare a table for this, then it will be easy. Okay, first we can make AB here. And then we can make C bar. Okay. After that, we can make a B plus C bar this. And then A, B, C bar. Okay. AB is here 0. This is 0. This is 0. This is 0. 0. 1. C bar is 1, 0, 1, 0. Then we can take cooperation between this AB and C bar, and we have to take no operation between these two. Okay. This is AB, C bar O is 1, but when you take no, it is 0. Here 0. Then this is 0, then it will be 1. This is 1, 0, 1. It should be 0. This is 1. 0. It is 1, 1, it's 1, but here 0. This is 1, 0, 1, it's 0. Okay. Next one, we have take A, B, and operation between these two. And this is 0, this is 0, 0, 0. Yeah, it's 0, it's 0, this is 1, this is 0. Okay, now we can draw these timing diagrams. For P, and here we can draw lines to separate these things, these regions. Here we have one, Okay, then when we can draw P, here this is A1. Okay, now this one is A1, B0, C0. A1, B0, C0. During that time, this is P, and this is P, and this is Q. Okay, then we can draw P according to this column output. Then during 1, 0, 0, 1, 0, 0, 1, 0, 0, here P is 0. Okay, the next one, 1, 0, 1. 1, 0, 1, then at that time P is 1. 1, 0, 1, P is 1. The next one, 1, 1, 1. 1, 1, 1, it's 0. Okay, next one, 1, 1, 0. 1, 1, 0, it's 0. This is 1, 1, 1. At that time, it's P is 0. And 1, 1, 0 also, it's 0. Next one, 0, 1, 0. 0, 1, 0. Here also, it's 0. This one, 0, 0, 0. 0, 0, 0, again 0. This one, 1, 0, 0. 1, 0, 0. Again, it's 0. This is 1, 0, 1. 1, 0, 1, it's 1. 1, 0, 1, it's 1. Here, 1, 1, 1. Again, 1, 1, 1. 0. And after that, here 1, 1, 0, 1, 1, 0, 0. This is 0, 1, 0, 0, 1, 0. Again, it's 0, 0, 1, 0. Yes, 0, 1, 0. And this is 0, 0, 1. 0, 0, 1. Yeah, it's 1. This is 0, 0, 0. This is 1, 0, 1, 1, 0, 0. 0, 1, 0, 1, 0 time is 0. This is 0, 0, 0. Again, it's 0. And last one, 0, 0, 1. 0, 0, 1 time it's 0. It's 1. This is P. Okay. Then Q. Q is all the time 0. Only it's having 1 at 1, 1, 0. Okay. Then Q here, it's 0. This is 1, 1, 0. This is 1, 0, 1. Again 0. This is 1, 1, 1, 0. 1, 1, 0. It's 0. Sorry, 1, 1, 0. This is 1, 1, 0. 1, 1, 0. Then it's 1. 1, 1, 0. And here, in this region, it's 1, 1, 0. It's 1. And this is here also we don't have 1, 1, 0. Here also we don't have 1, 1, 0. Here 1, 1, 1. Here 1, 1, 0. This is again this will be 1. This is 1, 1, 6, 0, no, no. This down. The previous cases that here V is 1, because 1, 0, 1, 1, 0, 1 is 1. Here 1, 0, 1, again 1, 0, 1. Here it's 1. This is 0, 0, 1. 0, 0, 1 also. 1. Okay. State 3, advantage of digital circuits over analog circuits. You know that many reasons are there. What are the advantages? Okay. Then it's compact. Okay, you can see this. Any problem? It's okay. Okay, then we can go to the next one. It's compact, low power, and low cost. Design and this is for some circuits this might not be true, but someone the high accuracy may be there. Okay, this is not a big one. This is, you know, that prove that one form of De Morgan's theorem could be obtained from the other by applying the principle of duality. Okay, we can. This is the same one. And what are the things we're going to change? Applying principle of duality, we have to change this plus to dot and this dot to plus. Then you have the other one. You're starting from this one. Then when you apply principle of duality to this one, we receive the second one. F1 A bar B bar C plus A B bar C F2 A bar Okay, shall we solve this one first? Because when we have this type of things, and you can minimize this one, keeping the top bar there. But other way is that we can first apply this top bar. You can break it using De Morgan's theorem. Then we can try the other things minimized. Okay, shall we apply De Morgan's theorem first? Then we can break this in 1 into 2 terms. And this is A bar B bar C dot A B bar C. Okay. Even though after minimizing by K-map method, if it could be simplified further using Boolean method, do we simplify further? Okay, Didi, thank you for asking this type of question, that she is asking that after minimizing using K-map method, still you can see that possibility is there to minimize further using Boolean algebraic methods. But in practical situation, if you are going to design a circuit, in practical situation, if you are going to design a circuit, yes, you have whatever the way that you have to minimize using whatever the method. But for the examination, if you are asked to do minimization using Carnap method, that answer is enough. In doing further minimization, you will not earn any mark. Then don't waste your time. Do whatever the thing that asked to do. Otherwise, that you are free to do whatever the. Okay, then we can break this one into, this is A plus B plus C bar. Here we can break this one into 2, A B plus C bar. Okay. Then there is no other way. We have to multiply all these things by this way. This is when I multiply this one from A, this one, this is AB and AC bar plus this one. This is AB plus BC bar. When you multiply this one, this is ABC bar and C bar. Okay, then considering this C bar terms first, we can take C bar out. Then inside we have A, B, AB plus 1. I took all these things out, but because when I see C bar here, when I take C bar out, here is 1. Then this whole term will be 1. Okay. And what is remaining? 2 ABs there. With these 2 ABs, we can write 1 AB. This one. And finally, this is AB plus C bar. Is it okay, this one? Here also we can apply De Morgan's theorem first. Break this one into 2. Then A bar plus this one is having top bar. This is plus. This one A plus B plus C. Okay. Then we can break this one into 2 considering this point. Then you can see A and B plus C. Okay. We are putting De Morgan's theorem, we are applying De Morgan's theorem to this term. Then we can break this one into 2. Then in between these 2 terms, this one and this one separately is coming there. And this plus should be dot. This is A double bar, B plus C double bar. Then this is 1. Okay. Then here we have, there's no need to keep this one. A plus B plus C. And this is AB plus AC plus A plus B plus C. Okay. From these 3 terms, we can take A out. And inside that, we have B plus C plus 1 and then B plus C. Then finally, we have A plus B plus C. Because this is 1. Here also same thing we can do. Can apply De Morgan's theorem to break these 3 into 3 terms. First here we can see this plus. This is 1 term. This is 1. This is another one. Because here we have O here. Then we can break into 2. A plus B bar C. Sorry. This is dot ACD. Okay, then we can apply De Morgan's again to this one. And this is A plus B bar plus C plus A B bar plus C bar D bar. This is bar. Then outside we have ACD. Here to solve the this bracket first, we have this A. Then again we have to apply De Morgan's here. Then we receive inside the bracket AB dot C bar D bar. Still we have to keep this one inside until we find a solution for this part. This is AB. We can apply De Morgan's theorem for here. It will be C plus D. So, ACD. Okay, then we can keep this part inside this bracket. We can multiply this. This is ABC and ABD. This is ACD. We can, shall we write one step? Removing this one? No, it's not necessary. So we can remove these two brackets also. Here we have plus. And finally, we can multiply all these things by ACD. Then this is, when we do it, this is ACD. This is AB bar CD. This is again ACD. This is ABC already there. Then this is ABCD, ABD, ABCD. Okay. Then again, this ACD, we can write one. This ABCD, we can write one. Anyway, we can take ACD out. This is 1 plus B bar, 1 plus B plus B. Then the whole thing will be 1, this part. Then the final answer is ACD. What about this? The first one is okay. The second one is also okay. Shall we try this third one? What do you think? Okay. We can, I think, there is nothing new from this first one and second one. But third one, there are something, and we will try this third one first, and we can go down. And if we have enough time, then we can come back to this one again. Okay. First one, A bar B C D, A bar B C D. This is one, A bar B C D. The second one, A B bar D, A B bar D. This region. Next one, A B bar C bar, A B bar C bar here. This one, A B bar C bar D, A B bar C bar D is already there. Okay. We have two don't care terms, A B bar C bar D, A B bar C bar D, and here this one is mentioned as don't care terms also. And it doesn't matter, we have already there. But anyway, when we have these two things together, we have to take this one essentially. And then finally, A, B bar, C bar, D bar. This one is also don't care. But here we have 1, then we can't take it as 0. Okay. This is 0, 0. Okay, then how can we minimize this one? We can mark this one. What is this? A bar, B bar, C bar. And there is no other one adjacent. Then because of that, we have to take this one as it is, A bar B, C, D. So this is A B bar, D. And finally, this is the answer. Equals B bar, B bar, C bar, A B bar, D, A bar, A C D. And what are the flip-flop types we have? We have this latch, clocked RS flip-flop, JK flip-flop, and D-type flip-flop. This truth table for this RS latch. Here we have RS. This is Q plus 0, 0, 0, 1, 1, 0, 1, 1. This is Q. This is 1, this is 0, and this is forbidden. We can't do anything here. Okay. Then when we take this one, this notation is then this is because we have this clocked input there, then we have to have this notation like this. This is 0, 0, 0, 1, 1, 0, and 1, 1. This is QN, we received previous one. This is set, this is reset, and still we don't have solution for the last combination. JK flip-flop, this is J, K, and with this, we are finding a solution for this last combination. That is the difference between clocked RS and JK. This is 0, 0, 0, 1, 1, 0, and 1, 1. This is previous, 0, 1, this is QN bar. D-type flip-flop is the simple one. We have only single input. This is Qn plus 1, 0, 1. We have 0, and we have the same values at the output. What are the issues of RS/? We have two issues there. The first issue is the first one. The input values could not be given simultaneously. This is the first issue. Second issue, the last combination. One. Could not be used. We can't use last combination, and we cannot give values simultaneously. At the same time, we can't give values. For the solution for first one is blocked RS flip-flop. The solution for the second one is JK flip-flop. Construct a D-type flip-flop is a very simple one. This is JK, and this is clock input, Q bar. Giving this additional part here. And finally, we have this. Then this is the resultant D-type flip-flop. We have D clock and Q. Q bar. Design a frequency divider circuit using rising edge trigger flip-flops, which divides input clock frequency by 16. Okay. What we have to do here? What is the circuit we have to design here? How many flip-flops do we need? Because it's mentioned it's divided by 16. Then how many flip-flops should be there? Yeah, if we have only one flip-flop, then we can divide it by 2. Then This is number of flip-flops. Divide by, if you have first flip-flop, this is divide by 2. 2 flip-flops, divide by 4. If it is 3, divide by 8. If it is 4, divide by 16. Okay. Then we have to draw 4 flip-flop circuit by using 4 rising edge triggered flip-flops. Then we have to use rising edge triggered flip-flops. And this is the clock input. Okay, then when we give clock input here, the frequency is F. From this output, we will receive F by 2. This is F by 4. This is F by 8. And from this, we can take F by 16 output. here that in this case that we are not asked to draw timing diagrams, then because of that, this is enough. But if you are asked to draw the timing diagrams, then you have to draw clock frequency timing diagram and then A, B, C, D. Then by these timing diagrams, you can decide whether A is having F by 2, F by 4 like that. Then you can, finally you can write from output D, according to the timing diagrams, we are receiving F by 16 signal. Then because of that, this is a frequency divide like that. Okay. But in this case, it is not necessary. Okay. Then the same thing here we have to do. But when you have this one, you know that this is rising edge triggered flip-flops. And we have to design up count. It should be up count, and we have to use rising edge triggered JK flip-flops. Okay. When we copy this one, there are certain problems. Here. And this is clock. And we can draw timing diagrams for this one. This is clock signal, and we can draw a couple of ones because it's not necessary. Again, it is not asked to draw the timing diagrams, but anyway, that we can draw the timing diagrams to show that the output of this one. Okay, these are the clock signals. And for A, B, C, D, we can draw this one. Initially, we can assume all A, B, C, D outputs are at 0. And this rising edge triggered flip-flop. Because of that, flip-flops will be triggered at these rising edges. Then according to the clock input rising edge, A will be triggered. And then we can draw A. Then here initially it will be 0. Then this will be triggered at the rising edge. It's coming like this. At this edge, it has to trigger again. Then A is going like this. Okay. Then B will be triggered at the rising edge of this one. Then we can draw B. Here B is coming up. And at this edge, we will be triggered again. And here it's coming down like this. C will be triggered at these rising edges of B. Then we can draw C. Initially it's at 0, and here it will be triggered. And here it's coming down like this. Then D will be triggered at this edge. We can draw D, 0. Then after that, it's going like this. Because we have to draw these type of things for at least a couple of clock pulses, then we can show that what type of counter this is. Okay, and to do that, we can put numbers here. And this is 0, 0, 0, 0. The next one is 1, 1, 1, 1. Then this is 0, 1, 1, 1. Then this is 1, 0, 1, 1, 0, 0, 1, 1, 0, 0. Sorry. 1, 1, 0, 1. This is 0, 1, 0, 1. And here it is 0, 0, 0. And showing these values, you can make a small table, put in this B, C, D values, starting from 0, 0, 0. Next one is 1, 1, 1, 1. Then next one is 1, 1, 1, 0. This is 1, 1, 0, 1. And 1, 1, 0, 0. Then 1, 0, 1, 1. What is the last one? It's 1, 0, 0. Okay. You can write like this. Then you can show these are the numbers. This is 0 and 15, 14, 13, 12, and 11. Based on these values, you can say this is down count. Okay. According to the resultant values, we are taking from A, B, C, D. Then the circuit is down count. Then, but here we are asked to design up count. The 4-bit is there, A, B, C, D, those things there. Then we, based on the timing diagrams, okay, then we can do this modification and we can say this is Q bar, this is A bar, B bar, C bar, and D bar. Then we have to take outputs from B bar, C bar, B bar, A bar. Then down up counter will be there. Okay, now Now we have this sub count, and you can consider it something like this. This is clock. From these lines, B bar, C bar, B bar, A bar. This is 4-bit up count. But then is asked to connect a 7-segment display using a BCD 7-segment decoder. Now you know that BCD 7-segment decoder, when we use this BCD 7-segment decoder here, it's having this B, C, B, A inputs and these 7 outputs. This is BCD2, segment decoder, and here we have our display here. Like this. And we have this output lines that we can connect. Here it's expecting 4 lines. Then we have these 4 lines. We can connect these ones straight away. But you know that here with our this count starting from 0, 0, 0, 0, and it's going up to this is 8, and this is 9. Beyond 9, it's having separate set. And this is, sorry. It's having 1, 0, 1, 0. That is that is 10. Then after that, go like this up to 15. Okay, this is 0, this is 8 and 9, this is 10, this is 15. Up to this one, we can display from 0 to 9. Okay, but after for this one, we don't have meaningful. Numbers. Why? Because from the 7 segment display, we have the facility to show from 0 to 9. And when we connect 4-bit counter like this, it's having full spectrum from 0 to 50, 0, 0, 0 to 1, 1, 1. But up to 9 from the display, but the counter is working like that, continuing from 0, 0, 0 to 1, 1, 1, 1, showing all 16 combinations. But from this all 16 combinations, for this first 10 combinations, we have meaning. Then it shows 0 to 9 on the display. But beyond that, 10 to 15, those 6 ones, when we have those 6 ones coming, those outputs coming from the counter, on the display, we will have the different jargon things. It's not a meaningful. Okay. Here we have 10 values, 10 combinations, and here we have 6 combinations. Altogether, we have 16 combinations. Is it okay? You understand this one? But first we have to design this one according to the question. Design a 4-bit up count using Rice-Gate triggered JK flip-flops. This is the answer for that part. But after that, connect a 7-segment display to the counter using BCD 7-segment decoder. Then again, it is not necessary to draw this diagram. Then it will waste your time. Then you can take it as a box. Then inside this box that you have designed this one, there is no problem. You can take this one as a block, and the BCD 7-segment decoder is also you can take as a block. Then you can connect these 2 blocks, and you have to show only the connection lines. What are the meaningful results which would be seen on the display? Here we can see, and we can mention it like this. And when you have a question like that, it's not necessary to write all these 16 combinations there. You can save your time. It's obvious that when you write the first combination and the last combination, and maybe the couple of those things, and in between you can put these dotted lines showing that it's continuing. But when you write these 5, you have to write those values, at least for a certain combinations, to show that pattern. Because here, when anyone sees this one, 0 to 15, 14, 13, like that, then they can understand that this pattern is there, and the student is knowing all these things, and he has understood all these things like that. That understanding will be there. Then you have to show that you are knowing all these things. Because anyhow, you have to earn the marks. To earn the marks, you have to show that you know those contents. It's up to you that most of the time that when you have the paper, those mark breakdown will be there. Then you have to think about the mark breakdown and spend your time according to the marks given for that particular section. If it is given that the very less number of marks for that particular section, don't waste much more time there. You have to give a very simple answer and go to the next section. And depending on the marks allocation and time availability, then you have to have your own method to answer the questions. You have to manage your time. And some of the students that I have seen that when we asked to do this one B6 segment decode this part, they have drawn this diagram again here for this 4-bit up counter one. Because they are doing this one because they might think that if they don't do that one, the marks will be loose like that. No, it's not necessary, but here that in the up, you have drawn it. And you can, if you want to make sure that you have done correct things, you can write something here, referring to the previous diagram like that. You can write it here. Then the marker will know about that. Okay, that is what coming from the tutorial. I think for this digital section, you might not have much more problems because we had enough time to discuss all these things, and we have a couple of lectures, and in between you have gaps. But for the analog electronics section, we didn't have that much of time to discuss and understand all these things. Maybe anyway, all the videos are there. You can refer those things. And in the evening, we will have the analog electronics tutorial. There we can have the discussion for these things. And if you have any kind of question, we can discuss those things in the evening. Anything coming from this one? Okay, if you don't have any question, we can finish this. We can end this session, and we'll meet in the evening. Okay, thank you very much for your participation, and with the quick informing quickly that you have come here, and thank you very much for your dedication, and we'll meet you in the evening. Until that, thank you.